Okay, so thank you very much for the introduction, and to Olivier, and Benjamin for the kind invitation and the opportunity to speak to you. So I want to talk, a little bit about nanomechanics and nanomagnetism and some related experiments going on in Basel in my lab. So the work I will be showing is actually done by a lot of these characters. Some of them are here. Floris, Nicola, and Boris are all here, and hopefully you had a chance to speak with them yesterday or the day before at the poster session. Okay, so actually I want to talk mostly about magnetic scanning probe microscopy and our work in trying to improve a version of magnetic force microscopy which involves nanowires. And then in the second part I want to talk about a kind of scanning SQUID microscopy that we're doing that we learned from a group in the Weizmann Institute and that we're now trying to apply to nanomagnetic samples and samples with mesoscopic transport. Okay, so let me start with the magnetic force microscopy. Uh, and let me start with a little sort of historical background. This whole idea of scanning probe microscopy, a lot of the things that we heard about yesterday with scanning NV centers, they all go back essentially to the early 80s when scanning probe microscopy really took off with the invention of the STM, which was really a revelation. It was the first kind of technique that allowed you to show atoms as they are on a surface, and it sort of produced this or established this idea that you could make images by just scanning a probe over a sample and measuring the response. And this became even more popular with the invention of the AFM, which was of course much more applicable to a whole slew of other samples because it didn't require a conducting sample. This also demonstrated atomic resolution some years later and basically gave birth to a whole series of PMs that we all know. So scanning SQUID microscopy, scanning Kelvin probe microscopy, magnetic force microscopy, and so on. Most related to this conference, of course, is magnetic force microscopy (MFM), which was developed in the aftermath of the development of the STM AFM, and this allowed basically for making images of very tiny magnetic structures. A more sensitive version of this, so basically an outgrowth of MFM, was MRFM, which was of course developed and invented by Dan Rugar, who's here in the audience, and this allowed you basically to make magnetic resonance images using a scanning probe microscope. So these were the first images made. Basically, I think it's electron magnetic resonance, and then later on, Dan showed how you could use this to do well, with Christian and me also, how we could use this to make NMR images of with very high resolution. Okay, the kinds of structures that required to make those kinds of sensitive measurements. Well, there's a lot of stuff that's required, as we saw in Cherk's talk last night. There's a very sensitive magnet that generates a gradient, and there's also very sensitive mechanical sensors that are required. So for the moment, let me just focus on the sensors. Basically, these are thermally limited mechanical sensors. The forces that you can measure with these are limited by the Brownian motion of these objects at low temperature and vacuum. And if you look at the spectral density of the forces acting on these things, they basically depend, of course, on temperature and on something on the mechanical dissipation, which is basically quantifying the energy that you lose per cycle in one of these mechanical oscillators. Now you can just write this down very simply. This is just the mass times the resonant frequency divided by the Q. So if you want to make these sensors better, if you want to make a more sensitive mechanical magnetic probe to do more sensitive magnetic force microscopy, then you need to reduce this number. And the minimum force sensitivity can essentially be written like this. Mark gave us a really nice introduction to torque sensitivity. The torque sensitivity of these objects is related simply by multiplying the kind of effective length of these things. So these can be in these kinds of structures. So this is a 100 micron silicon cantilever with about 100 nanometers of thickness. These can be very low, so they can be in the attonewton per root hertz range at 4 Kelvin. And we've heard in this conference how we can go even lower with other devices. You can also get you can do measurements in different ways. You can do amplitude measurements or frequency measurements, but the point here is that the limiting factor is always this temperature and this mechanical dissipation. Okay, so if you want to reduce this mechanical dissipation, you can just start asking yourself, what should I do? And it becomes very obvious very quickly what to do. So the mass is, of course, related to volume of the object. The frequency, if you just look at the Euler-Bernoulli equations for a singly clamped beam, is essentially related to the thickness divided by the length squared. And what we find in very thin structures which have a high surface to volume ratio is that the quality factor essentially goes like the thickness. Okay, basically we're limited by defects on surfaces. So if you take all of these together, you can sort of convince yourself that the mechanical dissipation goes something like the width times the thickness divided by the length, which essentially tells you should make some very long and narrow force sensors, which sort of makes a lot of sense if you were in Adrian's Bachtold talk and you saw that his very long and narrow nanotubes had force sensitivities on the orders of zeptonewtons per root hertz. It also means that if you scale all the lengths by some uniform factor, meaning you just shrink down your mechanical resonator and maintain the aspect ratio, you should be able to reduce your mechanical dissipation, increase your force sensitivity, and you win also in another way because your resonant frequency tends to increase. And this is very useful for practical applications because it means it takes you to higher frequencies and you become less sensitive to 1/f fluctuations that typically limit these kinds of measurements. Okay, so all of this motivated us to just starting to think about using very, very small structures for force sensing, and in particular for magnetic force sensing. So we started to work with bottom-up structures like these gallium arsenide nanowires, which are essentially single crystal hexagonal wires that are grown out of a wafer in an MBE chamber. Okay, and if you basically look at how the force sensitivity should scale, and the torque sensitivity, you basically win a lot by scaling these things down from the, say, micron scale into the deep into the nanometer scale. Okay, so let me skip this part. Now, of course, we're not the only ones who've realized this. So Rafi Budakian has, in the past several years, done a lot of very nice work with silicon nanowires, essentially using them as the mechanical transducers in MRFM, so in mechanically detected NMR, and they've shown some beautiful results which basically rival the results of the tobacco mosaic paper by Christian and Dan in 2009. This is essentially taking advantage of the fact that the silicon nanowire is an extremely sensitive force sensor, which oscillates at a very high frequency, taking the kind of 1/f surface-related noise is out of the equation. Nanowires are also interesting not only because of their extreme sensitivity, but because they're symmetric structures. So this is a very simple, as a consequence of this very simple idea, you can see that these kinds of symmetric structures, instead of having a single kind of fundamental node that's isolated, they typically have these doublet modes. So in the case of a perfectly symmetric nanowire, you should have two degenerate perpendicular modes. Of course, there's always some asymmetry in the structure or in the clamping that lifts this degeneracy, and so you have two modes for every order that oscillate in perpendicular directions. So this is kind of nice because this means you essentially have a vectorial sensor. So you have a sensor which can flex in two directions with essentially the same spring constant. So this was realized by the group of Olivier Arcizet and some others, and he demonstrated that this could be used as a very nice vectorial sensor in an optical field in this very nice paper a few years ago. And we also use this technique essentially to show that you can take a nanowire, scan it over a surface, and measure tip sample forces fields in 2 dimensions using these essentially as mechanical compasses. And there was also a paper by Olivier at the same time showing a very similar concept. Okay, but particularly for this conference, I'm interested in using these kinds of structures for magnetic measurements. So in recent times, we've tried to get nanowires which are functionalized with magnetic tips. So we got in touch with the group of Dominique Bogiard in Regensburg, who grows beautiful gallium arsenide nanowires with single crystal manganese arsenide particles on the end. Now these particles are something like 200 nanometers in diameter, and they're perfect crystals, and they have essentially a magnetic hard axis along the growth direction. So we've taken these wires, so you can see an SEM of one of these, so you see the hexagonal cross-section of the gallium arsenide, and then you see this kind of manganese arsenide hemisphere on the end. Now these objects, first what we did is try to measure their mechanical response in a magnetic field to try to learn what's going on with the magnetic state of this particle, and then later we tried to use these as essentially nanowire MFMs. Okay, so how do we do this? So we measure the motion of these nanowires using an interferometer, which basically measures the projection of the motion along this optical axis, so you can measure the two perpendicular modes. In fact, you can measure along essentially any direction if you misalign your interferometer, but I won't get into that here. So what you see here in this particular case is two very nice mechanical modes. So this is the doublet of the first mode, and you see that we have very nice cues and a nice separation between the modes, which allows us to essentially individually or separately address these mechanical modes. And so then what we do is dynamic cantilever magnetometry. This is essentially a torque measurement that like the ones that Mark introduced. And by measuring the frequency shift of each of these modes, we can pull out some magnetic anisotropy of this magnetic particle. Okay, so we monitor the two frequencies as a function of the magnetic field, and this tells us something about this, not that particle, but this particle here. Okay, so let me skip ahead. And so what we see is curves like this. So the blue and the red correspond to the two different modes oriented in the two different directions. So we're measuring torques essentially along two different axes. And we apply a magnetic field in this direction, and we see these kinds of curves. Now the first thing that you can take away from this, so you're measuring essentially this anisotropy, or these two anisotropies as a function of field. At very high field, what you should be measuring is essentially the magnetic anisotropy of the particle. And what you can see is in this particular case, the magnetic anisotropy is the same in the plane. And this is actually expected because this particle should have a hard axis perpendicular to the plane. And in fact, if you do simulations of a hemisphere of this kind of manganese arsenide crystal in this direction, and you ask what does the magnetization do as a function of the field, you see something like this. I guess I have to start it. You see that you have a saturated magnet in the beginning, and then at some point you see the entrance of a vortex. The vortex moves out, and then you see the magnetization reversing and going in the other direction. So because of this hard axis along this direction, the vortex is the favored remnant state at low field. In fact, when we take these simulations and we then simulate what the cantilever frequency response is, we get something like this for a nice particle with a hard axis along this direction and more or less hemispherical. And you can see we can very nicely match the measurements. So we're actually convinced that these kinds of structures that you see here and here correspond to the entrance of a vortex, that we have a vortex remnant, so at zero field, and then over here we have something that corresponds to the exit of a vortex. 200 nanometers. So this is not what you get in all cases. This is a particularly symmetric particle, and we have many thousands of nanowires on a wafer, and you can of course look at all of them if you want, and you can get particles that are much less symmetric, like this one, and you get very different responses. Now the first thing you should notice here is that at high field the two asymptotes go to different frequency shifts, and this means that there actually is an in-plane anisotropy. And in fact, what we find is that in order to match these kinds of curves, you have to orient the hard axis in some angle which is almost in plane. And from the growth, what the growers tell us, this is actually something possible, and so we think that this actually corresponds to a particle that has some kind of in-plane a hard axis anisotropy. And you can see that qualitatively the curves match quite well. So these are also rather rare, but the most common particles that we measure look something like this. And these can also be modeled essentially by a hard axis anisotropy along the growth direction and some kind of, let's say, non-perfectly hemispherical particle, so a more ellipsoidal particle which has some preferred axis in the plane. And this kind of particle essentially has vortices entering at non-zero fields, and at zero field it has some kind of net magnetization along the x-axis, so in the plane. So it's essentially at zero field, it's like a magnetic dipole. Okay, these are the most common ones. So okay, once we had this, we thought, well, that's kind of nice. We have an in-plane dipole, which which is remnant at zero field, and we can use that as a kind of very tiny MFM tip. So we started to scan this over some known field distribution, and our known field distribution is created essentially by a magnetic wire. So we pass a current through a wire. This produces a Biot-Savart field, and we then measure the response of our nanowire. So what produces the response is essentially, well, there are three interactions. The tip essentially has some monopole components, so we get some direct driving from the B field, from the magnetic field. It has some dipole components, so we get some driving due to the gradient of the B field, and we get some component due to the torque acting on this particle, on this magnetic particle. So what I should say is that we drive the nanowire with some current at the mechanical resonant frequency of the nanowire. That's how we do the measurement. So this is an AC field measurement. And what we get are responses as we scan over so we basically scan over this direction, a cut in this direction of the wire. We get some responses in the two modes that look like these points here. And we can very nicely fit these using these three components, so the torque, the monopole, and the dipole component. And then this tells us essentially what is the direction of our magnetic moment in our particle, so the net magnetic moment. So the dipole component, it tells us how much monopole component we have, and it tells us the direction of this dipole moment. And all of these numbers actually are quite good agreement with what we expect, and also what we learned from the dynamic cantilever magnetometry. So this first experiment is done at very high field, where the particles should be very simply saturated along the field axis. Now you can do the same experiment at low field, where, as I told you, you should have some kind of net magnetization in most cases in the plane, and we can also very nicely model the response of each mode. And we see that the magnetization, the net magnetization that we have, is something like 70% of the saturated magnetization. And we get out some angles which very nicely confirm that we have some kind of in-plane magnetization. So then you might ask yourself, okay, so how sensitive of a sensor is this? So we started to turn the current down and see how long it took us until we reached the noise limit, and that's what you see here. So we just reduced the amount of current going through the wire, and you continue to see a response. And then at some point down here, you reach the thermal limit. So basically, the thermal limit is just given by the thermal motion of the nanowire, which is limited at around a few attonewtons per root hertz, and sets this noise line right here. Okay, and you bring this down all the way down, and you can see that eventually you cannot distinguish the current signal from the noise. And so if you put in some numbers, you can find that basically we're limited by about 3.5 attonewtons per root hertz at 4 Kelvin, and that this corresponds at our working distance of about 250 nanometers to detecting a current of about 60 nanoamps per root hertz, which is quite a small current, and it corresponds essentially to a field measurement of 10 or 20 nanotesla per root hertz. So on the orders of what you've heard from the diamond sensors that were presented the other day. And this is simply just a mechanical wire with a little tiny magnet on the end. 4 Kelvin. Okay, so aside from mechanical sensitivity, there's also the fact that we have a very concentrated magnetic particle on the end. Now, in typical MFM probes, what you have is a kind of a dipole, or a long sheet of magnet, which is evaporated or sputtered on an AFM tip, and you end up in this situation here, where you have kind of a magnetic dipole, which with only one end interacting with the very strong fields of a sample. So essentially, what you have is a monopole that is sampling through the magnetic field. Now, in our case, we have a much more concentrated dipole, so we're much more in this limit. So instead of measuring some force response, which is essentially given by the magnetic field magnitude, we measure something which is given more by the magnetic field derivative. And this turns out to be quite interesting, because a dipole-like tip, which is really what we have, also according to our experiments, scales much better in terms of wavelength than a monopole-like tip. So what we have here is a plot from a very nice paper from the Hans Hug group, where he essentially plots the response of different types of MFM tips to essentially the K number of the magnetic modulation. So basically, as you go higher and higher here, this corresponds to higher and higher resolution. So what you can see is that a dipole tip basically doesn't respond to DC fields, and it responds better and better as the resolution goes up. So having a very dipole-like tip should enable also very high MFM resolution, and that's one of our motivations in trying to develop these devices. Okay, let me now kind of change gears and start talking about the second part of the set of experiments that I want to present. These are based on scanning SQUID devices. So I hope most of you are familiar with SQUIDs. Essentially, SQUIDs are superconducting loops which measure the Aharonov-Bohm phase produced by this magnetic flux going through the loop using a circuit that involves essentially two Josephson junctions. Now, what you can get with such a device is a really, really sensitive measurement of the flux if you sit at one of these linear parts of the interference fringes here. So you can have noises on the order of microphonon per root hertz, and this corresponds, when you divide by the area, to very, very nice field sensitivity. Now, of course, scanning SQUIDs have been around for a really long time. They've been around since the 80s, and they're very, very, very sensitive. And they've basically taken these three kinds of forms. So you can either have a SQUID loop, which is actually scanned on top of a sample, or you can have essentially a SQUID loop somewhere on a chip, which is then inductively coupled to a much smaller pickup loop, which is then scanned on a sample, or you can have some kind of hybrid system as shown here. And so there's been a lot of work in this, on this technique, and typically the work has in the past years has centered on these kinds of devices or these kinds of devices where people try to make pickup loops that are really, really small. That turns out to be technically difficult, and so we haven't had resolutions that are much lower than a micron, despite the fact that the field sensitivities can be really, really excellent. Okay, so let me talk about that. This is one example of one of these pickup loop SQUIDs, perhaps the smallest and most sensitive of these, I think from the Moeller group in Stanford. And what you see is that they have basically a patterned pickup loop, and then they have some very tiny, very sensitive SQUID inductively coupled somewhere over here on the wafer, and their pickup loop is made such that it's really at the edge of a wafer, and then they make it such that they can approach this wafer to their sample, and they do scanning probe. Now, just because of the size of all these elements and the fact that you have this wafer and this edge, it turns out that the distances, the working distances and the size of the loops and so on are on the micron scale, and so you have imaging resolutions that are sort of on the micron scale and up, and field sensitivities on the order of 100 nanotesla per root hertz. Now, there's been some work in trying to improve this also in my group, so I collaborated some years ago with a group in Tübingen and a group in Braunschweig who were making very, very nice nanosquids. So these are really tiny squid loops, which should have very, very high spatial resolution and very high field sensitivity. And we tried to turn the problem on its head and basically take squids that are patterned on a surface and then scan our magnetic sample on top. This was, of course, very nice for some very particular samples, like this very sharp magnetic nanotube, but not terribly practical for a general scanning probe experiment. So very recently, actually in 2010, the Weizmann group of Elie Zeldoff and actually Amit Finkler, who I think is in the audience here, invented a really nice, beautiful scanning probe method for doing scanning squid microscopy. Essentially, they take a quartz capillary, they pull it very, very thin so that you have essentially a tube which ends in a diameter on the order of 50 to 100 nanometers, and then they evaporate superconductor on the two sides to give some superconducting leads, and then they evaporate on the end a superconducting loop. And essentially what you have here is a squid loop where you have two Josephson junctions defined by these geometric constrictions. So this thing is really beautiful because not only is it very small, but it manages to take the squid really in very close proximity to the sample. And as you'll see later, this actually gives this technique some very nice functionalities on top of field sensitivity. So just to hit home how this works, this technique essentially involves pulling a quartz capillary, very, very narrow, and then evaporating some normal leads, in this case gold, and then some superconducting leads, in this case either aluminum or lead or niobium, and then a final evaporation over here to produce the squid loop. And now the most sensitive version of these are based on lead, which is kind of a nasty material to work with. But once you have the system working, you can get beautiful structures like this one, which actually have squids with diameters on the order of 40 to 150 nanometers. So this is actually a squid that was made in my own lab. So we've learned from Denis Vasyukov, who was in the Weizmann lab, how to make these, and we're now producing these squids and using them in scanning probe experiments. So the kinds of sensitivities that you can get here are really quite impressive. So you can get something like 5 nanotesla per root hertz. You can have 50 to 200 nanometers of spatial resolution, and you can operate to very high fields of up to 1.2 Tesla in these systems. Okay, so how do these work as magnetic field sensors? Well, basically, what you can do is plot the applied field along let's say, along this axis here. You can plot the response of this as a function of bias voltage and applied field, and you'll see these typical SQUID interference patterns. And from the period of these interference patterns, you can extract the effective diameter of these SQUID loops. And in this case, this is some data from our lab where you can see we have a loop on the order of 200 nanometers. And from the derivative of this interference pattern as a function of the field, you can see that there are some very sharp peaks here that we can, so very sharp positions here in field that we can use essentially as magnetic sensors. So if you replot this in another way, so you plot the current through the SQUID as a function of the bias voltage, and here for different colors you have different fields, you can clearly see that if we bias the system right around here, around 1.5 volts, we have a very, very sensitive magnetic field sensor. In this particular case here, if you work it out, this turns out to be something like 35 nanotesla per root hertz. Okay, so once we managed to get this stuff up and running, which took us a significant amount of time, we started to try to use these in experiments. And our first test sample was essentially a ferromagnetic nanotube, which is a system that we've studied a lot in my group. So this is a nanomagnetic system. It's basically a nanometer scale tube, which can support some interesting states. In particular, in the ground state, so near the remnant state that is supposed to be supported, is this vortex state, this so-called global vortex state, which is a flux closure state that doesn't have essentially any stray field. And there are some technological reasons for being interested in this, of course, because it means that if you have arrays of these, they don't couple, and that means you could have very high density arrays of these things. The other reasons for studying these kinds of structures is that they're predicted to have very robust and very reproducible reversal modes, which is also technologically very interesting. So all of this has been calculated in theory. The question has been in the last few years, can we actually create experimental structures that do these nice things? And this has been a bit of an open question in recent years. So we thought, well, why not take some of these ferromagnetic nanotubes and essentially scan their stray field as a function of applied field using our very sensitive SQUID sensor. So this is our version of a ferromagnetic nanotube. It's essentially cobalt iron boron evaporated on top of a gallium arsenide non-magnetic template. So we have basically a magnetic tube of 30 nanometers in diameter and about 200 nanometers in 30 nanometers in thickness and 200 nanometers in diameter. We put this down on a silicon substrate, and then we scan over it with our SQUID at different fields and look at the stray field. Now, if we have a global vortex state, what we should see is that the stray field essentially disappears. So what we first did is measured some quite long tubes, and we apply a magnetic field. In this case, we have a magnetic field applied into the board, and what we are measuring here is the stray field along this perpendicular axis. And what we see in the very beginning is that we have a saturated tube. Now, as we reduce the field in this direction and go into reverse field, what we see is essentially that this magnetization and the stray field, they essentially, the magnetization of the particle rotates into the plane and then comes back out into the other direction and saturates. So you see kind of a trivial Stoner-Wolfart behavior in the net. And we can very nicely model this, and it matches very closely to what we measure. And by taking these micromagnetic models and actually looking at what is the corresponding magnetization configuration, you can say that the tube in this case was essentially saturated down. Near zero field, it was mostly saturated along the axis with some vortex states on the ends, and in the other direction it was saturated up. And this is very nicely consistent with some other measurements that we've made, which I thought would come up, but are not here. No. yeah, these are very consistent with some other measurements we've made using torque magnetometry, where we can actually measure this kind of reversal and see the entrance of these end vortex states and see this kind of axial magnetization. I won't go into the details of that, but if you're interested, there's a paper on the archive. Now, what we did after that is to look at some smaller tubes, basically where we should, in principle, have at low fields a global vortex state. And what you can see, as I see I'm getting a little short on time, what you can see is that at low fields we have very, very low stray fields with this kind of yin-yang shape, and we can nicely model this again with our micromagnetic simulations. And you can see that actually this corresponds to a global vortex state which has some distortions due to imperfections in the geometry of this nanotube. So actually we think that the real nanotubes are in global vortex states, and that any stray fields that we measure, which are actually very small, are essentially due to small distortions in this configuration due to variations in thickness and asymmetries in these structures. Yeah. The size of the image, that's a good question. So I think this here is probably something like 3 microns or so. Yeah, but I should, maybe to get you a precise number, I'll tell you later. Okay. So let me skip. So again, this is very consistent with things that we measure in our torque magnetometry, where we see these global vortex states as we sweep the field in the torque signal, or we see the signatures of these states. So let me skip ahead because I see I'm running out of time. So I'm going to jump ahead to quite a lot. So I was too ambitious in what I wanted to show. But I do want to show one last thing, which is I think very promising for these SQUID sensors. So not only are these SQUID sensors excellent magnetic field sensors, but they're really excellent temperature sensors. So if you work near the critical field, you can plot these bias current, current bias voltage plots again. And here I have, instead of magnetic field, I have different temperatures near the critical field. And you can see that if you bias the system right around here, you have an excellent temperature sensor. And this temperature sensitivity is really spectacular. So this is something like 1 microkelvin per root hertz. This was actually demonstrated again by the Zeldorf group, who are really the pioneers in this sensor. And if you plot this in comparison to other temperature sensors, this is something like 4 orders of magnitude better than anything you can get. Now, the caveat, of course, is you have to work near the critical temperature, so around 7 Kelvin for lead. But in principle, you're able to measure dissipation of systems very, very sensitively. Okay, so we've done this, of course. You can actually get this thermal signal along with your magnetic signal, and it's very convenient. And I just wanted to show that here. So essentially here we pass an AC current through a wire, and we measure the Biot-Savart field by just looking at the AC response of the SQUID. And what you see here is a very nice signature, essentially, of the field being perpendicular on top of the wire. So we see the AC magnetic response here. If you look at the response instead of at the AC frequency, so at omega, you look at 2 omega, you start to see thermal signal. So this is essentially signal due to ohmic heating, Joule heating of current going through the wire. And then if you look at DC, you just get DC magnetization, so you get DC field, and we get images that show that this little thing here is magnetic. So this is actually a ferromagnetic nanotube. So what I want to show with this slide is that essentially with this single sensor, you can have really nice, you can actually have 3 separate types of contrast, which could be very useful for these kinds of magnetic structures, but it can also be useful for transport experiments, as the Zeldorf group has already shown. So there's a recent paper by the group in Science where they essentially use this thermal sensitivity to measure edge defects in graphene. And I don't have time to get into the details of this, but this could be really very promising for measuring transport in these kinds of mesoscopic structures. So let me thank you for your patience. I throw up some relevant references here on things that I talked about. So these things here and some things that I didn't get to talk about. And if you're interested, please check out this webpage. And as a final advertisement, let me just say that there are postdocs available. There's a postdoc fellowship available in Basel. So if any very ambitious PhD students are interested in research like this, please check out this website or come talk to me. There are some very nice jobs available. Okay, thank you very much. Yeah. Yeah. Okay, those are two excellent questions and actually kind of related. So how do we get the thermal contact? So of course, if you're in vacuum, as we like to be, there is no thermal contact between the sample and your squid. So what you have to do is introduce some exchange gas. So all of these thermal measurements are enabled by exchange gas, and you have to introduce the right amount of exchange gas because basically you need a stronger thermal contact to the device that you're measuring than to the environment, which is essentially coupled through the squid tip. But that's actually not so complex to do because the squid, so the leads are superconducting, so they're very well isolating, and this is a very narrow quartz tube, which is also very isolating. So actually there's quite a big parameter space where you can tune the thermal coupling to somewhere you want. Now, if you have too much thermal coupling, you can't get exactly what you said. You can get some feed through basically between the thermal signal and the magnetic signal. But if these things are small enough and your vacuum is kind of good enough, you basically don't have any feed through between these two. Now, what you can see is that there is some feed through of the thermal signal here into the DC, but that's of course expected because if I square sine of omega, then I get sine 2 omega plus some constant. Yeah. Yes, exactly. That's a very good point. No, I was really too ambitious. um, yeah. So basically, you're right. This is only a sensitive sensor at these particular fields. Now, the sensitivity is optimized here, but of course you can see you have some sensitivity all along these lines, and basically you have certain blind spots in the field that you cannot measure. Uh, 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 yeah, you cannot measure anything. Now that's for our sensor with two Josephson junctions. That turns out to be, we have enough working points that it doesn't really matter in most cases. But the Zeldov group has actually developed a squid with 4 junctions, where they can apply a voltage which can essentially tune this interference pattern anywhere smoothly along the field axis. And then you have a sensor for all fields. Of course, you're limited by the critical field, which is on the order of a Tesla, and above that you can't go. If you want to increase that, you have to work at lower temperatures, which is of course possible. Mm-hmm. Yeah, that's a good question. I don't know the answer to that question. Maybe the guy behind you might. So by the way, this is Amit Finkler who actually developed these. Yeah. Yeah, that's an interesting question. So when we first started to think about these wires, we were very naive and we thought hexagonal, we must have 3 modes. But in fact, it's not true. So any symmetric shape should always have 2 modes. And if it's symmetric, whether it's a triangle or a hexagon or a circle or whatever you want, they will be degenerate. And if you need some asymmetry either in the clamping or in the cross section in order to lift this. Now, if you look at TEMs of these wires or SEMs even, because of the MB growth, you'll see that there's always some slight difference in the hexagon. So one side is a little bit shorter than the other, and it's basically unavoidable. I think there are other systems which are more like the silicon nanowires from Rafi, which are actually much more symmetric. And Rafi, I think, had to work hard to make the splitting enough that he can address the two modes essentially by evaporating or depositing material on one side. Yeah. I guess so. The aluminum is a problem because it works only at lower temperature, so below 1 Kelvin, and the noise is flux noise that you get is also higher. So it's a nicer material to work with in the sense that you can get these much nicer looking squids, as you saw in the picture from Mitt's paper. So these actually look much cleaner. But because of the difference in the coherence length and the penetration depth, these can also not be very small. So they work at lower temperature. They're not as small, and they have higher noise. So the squid, the lead somehow has the right numbers for the coherence length and the critical field to make the most sensitive, highest resolution squid. But it is a nasty material, and it may be that we could develop other materials that would work at higher temperatures and be even more sensitive. But I can tell you, even just copying what they did in the Zeldorf group, it took us about 2 years. So working on a new material, that would be a challenging task. So the lowest order modes are these flexural modes, right? And that's what we couple to. And then the next order is something like the second order flexural mode, which I think I showed in the graph. And then eventually there will be torsional modes, but these are at much higher frequencies. Yeah. So as you go higher and higher, of course, spring constants get higher and you get worse and worse sensors, sensing modes, right? You mean the T scanning squid, this one? Oh, how do the fields compare? Sorry, say again? Uh-huh. Oh, how fast? Okay. So I think right now with the electronics that we have, because we have a series SQUID amplifier along the line and some filtering, we're limited around 40 kilohertz or something like that. But that's not something really fundamental. Like these squids, in principle, have really, really high bandwidths, and you can also make so you can imagine doing reflectometry on these things and going up to hundreds of megahertz or gigahertz. So in principle, I don't think there is a limitation in the frequency. There is some technical work to be done, but yeah. Yeah, I sometimes wonder whether we could do some of these sort of spectrum analysis of noise, as was discussed in the NV sensors with the squids, but we have a much, let's say, broader band sensor. So